Hello, everyone. Welcome to the HashiCorp Secure event. I hope all of you are doing good. My name is Narendra, and I work as a senior DevOps engineer with Ignite. And today we are going to talk about a journey towards implementing service mesh. So let's move to that. I'll share my screen, put this into presentation mode, and I think we are good to go. Before we begin this, I just wanted to share that we being backend developers, we are not very good at formal presentations. The rate at which we speak is equivalent to the rate at which we type on our keyboards. So if you see something amiss with this presentation, I've shared my contact details on this slide. You can just let me know, and I'll try to better myself for the future. So with that, we'll just move to talk for today. So we are going to speak about service mesh. We are going to talk about our journey towards implementing service mesh. So for the next 25 to 30 minutes, I'll give you or I'll be bombarding with you a lot of information about service mesh. So I hope it makes sense to you, and at the end you will be able to take something back. So with that thought, let's start. So agenda for today's talk is we'll first start with establishing what is service mesh, and then we'll have a look at the setup for which we are implementing service mesh, and then move towards the implementation where we'll discuss how we implemented this idea of service mesh into an actual solution. And then we'll have a look at the customizations or the fine tuning that we needed to do to meet our requirements for service mesh. And towards the end, we'll discuss a bit about the blue green or canary deployments POC that we did from service mesh. So moving on to the first one. So what is service mesh? A lot of members on this talk already must be aware of what is service mesh, but we could also have some members who are joining in for the first time. So for them, let's just have a brief overview of what is service mesh. So you can think of service mesh as this dedicated infrastructure layer that allows you to make your services connect to each other in a secure manner. So service mesh does this by providing an identity to each of your service so that they can establish a trust with the other services and connect with them in a secure manner. It does so by allowing some capabilities transparently, like security, traffic management, and observability without you requiring to bake them into your code. So what are these capabilities? Let's just have a look. So these are some of the advantages of features that service mesh offers. In the interest of the time, we'll not go into the depth of these features. Most of them are self-explanatory, but I just wanted to highlight is the ones in the greens are the important features that we have implemented. And ones in the orange are the ones we are going to implement in the next iteration. So why Consul and why not any other service mesh solution? The primary advantage we get from Consul is that it is cross-platform, in that it supports both VM and Kubernetes. And here at Ignite, we have workloads running both on virtual machines as well as Kubernetes. So Consul gives us a unified service mesh that covers both these platforms together. Also, Consul covers all the important service mesh features in terms of security, observability, or traffic shaping. Also, we get something called as intentions with Consul. So with intentions, the service admins can configure which service is allowed to talk to which service, and only those service would be allowed to connect, and any other traffic would be disabled in the network. So this pushes us towards zero trust security. Also, one important feature about Consul is the escape hatch overrides feature. With this feature, in case if there are something that Envoy supports but Consul has not yet implemented, we can even use those features by passing raw Envoy config via Consul to the Envoy sidecar. So we'll have a look at this in detail in the later part of the presentation. So this is one of the important features. And then Consul is already highly available, stable, been there for a while, and it's a proven solution. So it helps. And we are already using Consul for our service discovery needs, config management via key value storage, and Consul template for our templating needs. So it makes sense for us to extend this with a service mesh solution. Rather than going with another solution, just extend Consul to fulfill the service mesh requirements. Also, let's just look at some of the concerns with respect to service mesh. So service mesh is a complex setup. It requires some learning curve. Also, Consul becomes very critical now that use it for a variety of use cases, including service mesh. So we'll look at in the later part how we have implemented and how we overcome these challenges. So moving on. So we talked about service mesh, but how does service mesh actually work? So let's try to understand with an analogy. So let's say we have two services, a web service which speaks to an API service. With the introduction of service mesh, you'll have two sidecars, one each next to the service. So web service will have a sidecar next to it, and the API service would have a sidecar next to it. In Consul Service Mesh, we use Envoy as the sidecars. Uh, so the traffic from the web service would be going to this sidecar, and then this sidecar will securely transmit that traffic over the network to the destination sidecar, which will then pass it on to the API service. So all the shifting, all the routing of the traffic is done via the sidecar, but the logic to where to route, how to route is dictated to it by a console through the Envoy XDS API. So you can think of Consul as the control plane, which controls how the traffic would be routed, and you can think of Envoy as this data plane in terms that it does the actual routing of the traffic. Also, a bit of other terminology around service mesh. So the application for the sidecar is called its local app. So for this sidecar, the web application would be its local app, and for this sidecar, the API application would be its local app. Also, the application that makes an outbound connection is called the downstream application, and the application which receives the traffic inbound, it's called the upstream application. So moving forward, so we spoke about Envoy in the last slide. Envoy as our sidecar proxy. So how does Envoy look like? Let's have a look at the high level architecture for Envoy. So continuing from our past analogy, let's say the web service sends a traffic to the sidecar. So the web service, which is the downstream service, it will send a traffic to the Envoy sidecar. Now Envoy works in a threaded model with one thread dedicated to the server management, and rest of the threads handle the actual data. So the traffic, when it comes to Envoy, one of the worker threads will accept the traffic via the listener module. So the listener is the first component with which the traffic interacts. So listener accepts the traffic inbound, and then does some pre-processing on the request and runs it through a set of filters like the router filter, the rate limiting filter, distributed tracing filter, logging filter, authentication and authorization filter, and so on. So after applying those filters, it passes on it to the cluster. You can think of cluster as a collection of endpoints of a similar or a logical service. In our case, we can think of cluster as a collection of instances or endpoints for the API service. So once the downstream or the web traffic comes to Envoy, the listener will accept the traffic, apply set of filters, and then pass it on to the API cluster. And from API cluster, one instance or one endpoint would be selected by the chosen load balancing strategy, and then the traffic would be passed to that instance, that API service instance upstream. So this is the high level or overview of the how Envoy works. So now we established what is service mesh and how does it work. Let's just also have a look at the setup for which we are implementing service mesh. So we are implementing service mesh for Egnyte. Egnyte is a content collaboration, security and governance platform. We serve more than 17,000 customers worldwide, and the service for which we are implementing service mesh at Egnyte is the Egnyte Object Store. You can think of Egnyte Object Store as the heart of the Egnyte ecosystem or Egnyte platform, in terms that it handles the entire content life cycle for the our customer data. Let's just have a look at the traffic stats. So we observe more than 1 million requests per second for our object store, and there are more than 200 queries per second on the database. This can also be validated via these functional stats. We have more than 100 petabyte of customer data at rest, and we ingress close to 1.5 petabyte of data per month, and we egress or the downloads are more than around 7 petabyte per month. So this is constantly growing, and this is a very high traffic app. and hence we have the need to ensure the traffic to the service is always safe, secure, and legitimate, and verified and validated. So for that reasons, it's important to have a solution like Service Mesh for it. And this is one of the reasons why we implemented Service Mesh for the Ignite Object Store. So this is the high level architecture of the object store. So the object store functionality is bifurcated into pools depending upon the functionality it offers. So we have one pool that handles the uploads, one pool that handles the download. We have one compute pool that handles all the background jobs, and we have one pool for filers. Filers is the you can think of filers as this staging area where all the uploads are staged before they are persisted to the end storage. So this object store interacts with a lot of middleware, like we make a very heavy use of caches, databases, both both RDBMS and NoSQL. We also interact with a lot of storage solutions, like on cloud storage solutions like AWS, Azure, GCP, Alibaba, and others. We also make heavy use of PubSub queues to process a lot of asynchronous tasks, secret managers, config management solutions, and so on. Also, there are a lot of internal services that connect to the object store, like video services, preview services, audit, billing, and so on. Also, the end user or the customer can also access the object store by logging into his favorite browser and access the object store. He can also install the desktop app and use Ignite as his file system. Also, a lot of customers use migration app to migrate data into Ignite from another providers. So this is the high level overview of the Ignite object store. You can see the amount of scale and amount of complexity and different components that it interacts with. So to ensure all these interactions are secure, we augment each of these components with service mesh solution via Envoy sidecar, which are powered by Consul. So this ensures all the traffic on our network for the object store is always safe and secure. Now that we saw the architecture for the object store, let's just also have a brief overview of how Consul works at Ignite. So like we discussed, we have workloads both running on VM and Kubernetes. So we have the cluster configured both at both ends. For the VM, you can see it's a standard highly available Consul setup with each node having a Consul client that connects to the Consul servers. For Kubernetes, we have installed Consul via the standard Helm chart, and each pod has this sidecar running with it that handles all the service mesh functionality. Also, one thing to point is that we do not have any Consul servers installed in Kubernetes. Rather, Kubernetes connects to the Consul servers on the VM side via the external servers configuration. So with this, what we get is we get the entire entire platform comprising of both VMs and Kubernetes into a single Consul data center. So that is actually helpful for us. So a bit of stats around Consul. So for the VM infrastructure, we have close to 4 production DCs. Each has its own Consul clusters, and we run more than 500 Consul client nodes per data center. The functionality which we use Consul for is we use Consul key value for a config management. We use Consul template for a lot of our templating needs. We use Service Mesh, which we are discussing in this presentation. We also make use of the Consul API and Consul SDK for our various needs. So that's about the VM infrastructure. Similar to the VM infrastructure, Kubernetes also has one Consul cluster for each production DC. It's a pure service mesh setup which connects with the Consul servers on the VM side, and it's being installed with the standard Helm chart. So now we established what is service mesh, and we also had a look at the setup for which we are implementing service mesh. Now let's have a look at the how we implemented or how we moved from a idea about service mesh to an actual implementation. So before we begin, we just wanted to point out that the entire configuration for service mesh at Ignite is done with infra code perspective, so that the solution is reliable, consistent, and could be easily replayable in case of any issue. In case of any let's example say that there is some issue with the infrastructure, we can, or there is a config drip, it could be automatically remediated with the infra code approach. we have done that with the help of Puppet for VMs. We are using Helm for Kubernetes. And one thing, with this implementation, we also wanted to uh, uh, get this working in a safe manner. So we have separate flags for switching on and off the sidecars, and separate flag for routing of traffic via those sidecars. Now, why do we have these two separate flags? Uh, uh, with the flag to switch on and off sidecars, we get an opportunity to beforehand switch on the sidecars, do all our checks, validate them, and see if they are functioning correctly. After that, we can just route traffic to those sidecars via switching another flag. Also, in case of any unforeseen issue, we can always route the traffic away from those sidecars via switching of the routing flag, but we'll still have those sidecars available for our debugging purposes. So for that reasons, we have two different flags for routing and switching on the sidecars. We also deployed sidecars with zone awareness config. Now at Egnyte, it's a very high traffic app, and the object store at the object store, we constantly have some uploads or download ongoing, and a lot of them are large uploads. So any interzone traffic would incur a very high cost. So with zone aware, we have deployed service mesh with zone awareness to ensure that the traffic for an entire request will always stay in the single network zone, and it will save us the interzone charges. With that, we also configured Envoy with hot restart on for our virtual machines. So the default configuration for Envoy with Consul Service Mesh would drop connections when Envoy is restarted, but we didn't wanted that. So for whatever reason, in case if we had to restart Envoy, we want it to handle connections gracefully, in terms that it will not drop connections and wait for the existing connections to complete, and then move forward. So for that, we have configured hot restart for Envoy. Another important aspect that we need to keep in mind, which we also had to take care of, was tuning the timeouts. So by default, Envoy comes with some default timeouts, but those might not be suitable for our use cases. For us, especially this Envoy route or request timeout was of 15 seconds, but we have frequent uploads and or downloads, and a lot of them are long running. So for that reason, we had to tune this 15-second default timeout for to make it suitable for our requirements. Now with this, we have configured service mesh in our environment via Puppet Helm. We also have flags to switch on and switch them off. We have configured hot restart to protect us against dropping connections. We have tuned the timeouts to make it suitable for our requirements. But after that, we also did some functional and performance tests to validate that the solution meets our requirement, is correct, and we do not see any errors or any regression issues happening due to the introduction of service mesh. So we did some functional and performance tests. After that, we also have our own monitoring dashboards, and we have also configured logging and alerting. This is useful in terms that if there is any issue on the system, we get to know it beforehand, before the end customer notices it. So we have implemented our own solution for that. Also, we have configured a failover strategy for going live. We'll discuss a few of them in the next slides for better understanding. So in the last slide, we spoke about the testing which we did. So these are some of the test cases that we ran to ensure that service mesh doesn't introduce any functional issues. Apart from this, there are various other automated test cases that run in the our infrastructure, which due to security reasons I can't share. But these are some of the important test cases that we ran to ensure that the functionality is not hampered with the introduction of service mesh. Also, with the performance team, we measured the response time and the throughput post introduction of service mesh, and we didn't saw any barriers towards implementing service mesh. So let's move on. We also configured monitoring with the Prometheus Consul SD plugin. So Prometheus can auto discover any services that has been introduced in Consul. So with that, we automatically have any service into monitoring by default whenever it is configured in service mesh. Other thing that we wanted, we had to tune, was increasing the maximum connections per client for the Consul client on the Prometheus node. Our application being a very high traffic app, we have lots of nodes, sometimes 500 to 600 nodes at peak hour traffic hours. And the default connection limit on the Consul client for the Prometheus node was 200, which was not sufficing our requirement. So we had to tune it as per our requirements. So the maximum connections per client on the Prometheus node for Consul client had to be changed as per our requirement. So that was the change we did. Then we have configured our own Grafana dashboards, which has all the important metrics in terms of the number of requests, number of connections, rate at which connections are getting formed, the rate at which requests are getting formed, how many of the requests were successful or 2xx, how many of them were errors, in terms of how many of them were 4xx or 5xx. We also measure the latency for our requests in terms of percentiles. So we have numbers for P99, P90, and P95 percentile. We also have matrix for circuit breakers, matrix for timeouts, and then we also have matrix around how the certificates are managed for Envoy via Consul, and the uptime and all of the other information. We have configured logging with Puppet and Logstash. So any new app that is introduced to Service Mesh will automatically have logging configured, and all these logs are then pushed to a centralized ELK solution where we can do an detailed analysis on them. For alerting, we have dedicated Slack channels for alerting. We also get page for critical events like sidecar down or traffic anomalies. So we have ensured that while we have a strong service mesh solution with which take care of all the important aspects, we have also ensured a strong monitoring, logging, alerting, so that we do not allow any issues to seep into the end customers. So we have taken care of that. Now let's just speak about the rollout approach that we took. So we followed a slow rollout with failover support. This is to ensure that with the introduction of service mesh, if there are any issues, our end customers doesn't see it. So our L1 and L2 proxies have direct connectivity to the our application as backup. So in case the primary or the Envoy side, which is the Envoy sidecar, if it fails a health check, or if it goes down, then the traffic is routed through these backups directly to the application. So the end customer doesn't see an issue, and we can quickly fix the service mesh issue in our infrastructure. Also, a lot of microservices connect to the object store. So for those microservices, also we have a flag in Consul KV, with which, in case of issues, we can quickly move away the traffic from those sidecars and allow the direct connectivity to the application. This is done via the applications long polling the Consul KV, so they can quickly update any changes in the Consul KV. So with this the aim is to ensure that we release something like a complex solution like service mesh, which gives us a lot of advantages in terms of security, observability, and traffic shaping, while also ensuring our end customers doesn't see any issues. And this is a temporary arrangement. Once we are confident about service mesh, we can remove this. We'll be removing these backups to ensure all the traffic goes only via secure service mesh channel. So this is about the rollout. So we spoke about the our implementation journey. Now just let's have a look at the customizations that we had to make so that the service mesh works correctly according to our requirements. So one of the important customization that we had to do was the graceful handling of the sidecar lifecycle. So by default, when Consul injects the sidecar on the Kubernetes pod, it starts at the end after all the application containers have started. Now this is a bit of problematic because our application being high traffic, they start making connections to dependent services as and when they start. For the time which this sidecar is not available, the application containers will get connection refused for connecting to the dependent services. In fact, in our QA environment also, we get thousands of errors for each pod when it starts up, because it is not able to connect to dependent services via sidecar, because the sidecar starts at the very end. So for that reason, we fork Consul to create our PR that will solve this problem for us. So with this PR, what we have done is we have configured the service mesh sidecar to start as the first container in the Kubernetes pod and the last container to be stopped. So due to which, whenever our application container starts, it will always have the sidecar available to connect to the dependent services. So this PR is helping us achieve that. These are some of the other customizations that we did. From our Consul advantages slide, we spoke a bit about escape hash overrides. So we have used escape hash overrides to achieve a lot of our features uh, that were not present in our Consul. So some of them are now present in Consul, and we have done away with some of this and have used them directly via Consul. But just wanted to highlight that when those features were not available via Consul, we had used escape hash overrides to pass in raw config via Consul to Envoy and get these features implemented. Apart from that, one thing which we wanted to highlight was we have our own custom build for Envoy for CentOS 7, since we are using CentOS 7 in our infrastructure, and due to the glibc being run on an older version on CentOS 7, the latest versions of Envoy are not compatible with it. So along with the Envoy help from the Envoy community and these useful links, we bypassed the TCP stats extension that was dependent on those outdated glibc versions and build our own binary for Envoy, custom binary for Envoy, similar to the custom binary that we have for Consul to meet our use cases. So that was about the customizations that we had to do for our service mesh requirements. Now just let's have a quick look at this blue-green or canary deployment approach that we did with service mesh. So we did a small POC wherein we leverage service mesh to do blue-green or canary deployments. Let's just have a look at that. So initially, all the traffic would, or client traffic would always go on one particular version. But now let's say you introduce a newer version, a version called V2. With service resolver, you can, with the service mesh service resolver config, you can divide your versions into subset. You can have one subset for version 1 and the other subset for version 2. And with service splitter, you can route all your traffic to an existing or the current version, such that all the traffic would go to the version 1 and no traffic would go to the newer version. Then we can start sending some test traffic to the newer version with service router. Let's say we start sending test.ignite.com, that's test traffic to the newer version. We verify everything works on the newer version. It works as per our expectations. Once we verify that, we can slowly start gradually increasing the amount of traffic that we send for the newer version. For example, we can start sending 50% of our traffic to the newer version with the service splitter configuration. Once we are good with this and we see it is performing as per our requirements and has the correct performance, then we can gradually increase or send all the traffic to the newer version. Let's say we can send all the traffic to the newer version with this service splitter, sending 100% of the traffic to the newer version. Now there would be no traffic on the older version, and we can clean the older version. So now you'll have all the client traffic going to the newer version. So the aim of this POC was to ensure that we can use leverage service mesh for something like blue-green or canary deployments and send out our releases to customers in a safe and secure manner, and ensure that the newer version that we are sending out the customer does not have any performance issues, bottlenecks, or any functional issues. So this will ensure that the newer version that we are sending is safe, secure, and meets our customer requirements. So with this, we come to an end for our presentation, but that's one important slide that we still have to share. So, we wanted to thank some of the team members. We wanted to thank the DevOps infra and perf team at Ignite for moving or helping us move something like service mesh from an idea to an implementation. We also want to thank a couple of members at HashiCorp, Luke, Blake, David, and the entire HashiCorp community for helping us whenever we got stuck and helping us with our questions. And thank you to HashiCorp as well for the truly great products that you make. So with that, it's my time over here. If you like this presentation, then do have a look at the other blogs at Ignite as well. And with that, I'll take a leave. So thank you everyone for joining us for this presentation. I hope you can take something back from this. And thank you everyone for joining it. So Bye.